In today's presentation, I'm going to be talking about the concept of an operating system for complex discrete manufacturing. And I'll be talking about how we're applying Industry 4.0 technology to deliver flexibility and efficiency, specifically in complex discrete manufacturing. So let's take a brief look at the definition of complex discrete manufacturing. This chart shows the different types of manufacturing from repetitive, discrete, additive, job shop, process, and process batch. And what we want to specifically talk about today is discrete manufacturing. So an example of discrete manufacturing is an automotive plant where, as you can see, value or the product is moved down the production line and value is added step by step. What's also very important to note is that each product can be uniquely identified either by barcode or RFID on the pallet or RFID on the product itself. But as it moves through the process, we're able to identify the unique ID of that particular product as it moves down the production process. So this is not just an automotive concept, but there's many different types of discrete manufacturing, and this chart shows the different types of discrete manufacturing. So from machinery, aerospace, medical devices, agricultural equipment, industrial components, robotics. So there are many industries that adopt a discrete manufacturing process. And from our perspective, what makes it complex is that the product that is coming down the production line is not the same as the previous product. So you can build different types of cars. As we all know, you can custom build your car with different options within it. And each car that comes down the production line is unique to a specific customer. And that's what makes it complex. And so it's not the same product coming down the production line. It is actually different variations of that product that come down the production line. So let's just talk about some of the challenges that complex discrete manufacturers face. So one of the biggest ones is this fluctuating volume and output demands. And this is beyond the typical ramp up, ramp down cycle. This is where, as we experienced during COVID, an interruption where things had to stop, volumes were really low, and then actually demand was far higher than what was originally anticipated. And so what was actually needed was flexibility in the production lines to add equipment and potentially remove equipment to make it always run at an optimal level. Another element discrete manufacturers are challenged with is this complexity in the product. So as end customers want more unique and customized products, the concept of mass customization, as I illustrated with the vehicle, every vehicle is actually different. This is stemming and moving down to different products, medical devices, agricultural equipment, are all becoming specific and unique to a particular customer. So the product that is being produced is always changing. And so you need a system that enables quick adaptation to new products and quick process changes that can be made with minimal downtime, lowering skills, a lower skill level to make these changes. You don't want programmers to come in and actually have to hard code processes into the system, as an example. Quality assurance of manual processes. So many discrete manufacturing processes are a mixture of manual, auto, and semi-auto processes. And so obviously keeping the process security and the quality of the part, even when elements of the production process are manual, are really important. And this is where the system has to take care of a lot of that with different hardware elements, but also managing the process security of each process as it goes down the production line. What is really interesting is that many factories don't have live production visibility. So you have plant managers that only get information on the performance on their plant by hour, sometimes only at the end of the day or at the end of the shift. And in some cases, when the inventory arrives in the logistics warehouse, does the production manager actually get information on what was actually produced on their production lines? And so what we believe is possible and necessary in the production line of the future is live, accurate information that is presented to you based on your persona. So you could be a plant manager, you could be a maintenance manager, you could be an operator. That information needs to be shared with you on a live basis. Shortage or high turnover of operators is a key challenge that most discrete manufacturers face. So either not enough operators or a high turnover of operators, and in many cases, not enough skills within the operators to actually work on the shop floor. And so we need systems that are able to quickly train and onboard new operators, and also manage the risk and the quality of the product that is introduced when you bring new people onto the shop floor. The top-down approach has always been a challenge in most organizations. This is where, for example, systems and processes are implemented like ISO, some quality management systems, and inevitably these end up being tick box exercises and driven from the top down. What we believe is that we need to take a data first and a data-driven behavioral change approach where it starts with the operator. And we believe that by providing the right information to the operator with the right incentives around that information, you actually start to improve the performance of the shop floor from the operator up. And you avoid these top-down approaches that end up being tick box exercises. One of the key requirements, not in the future, but actually now, is to adopt new technologies like AI and machine learning onto your shop floor. But many systems, even if there is an existing system, an existing MES system, they are not AI or machine learning ready. And so you need to be able to develop a system that once data is analyzed, processed, and insights and outcomes are determined, that needs to be able to be fed back down onto the systems and onto the equipment, onto the shop floor in an easy way. You don't want to stop the line from producing parts for a week because you've discovered some insights that need to be changed on a particular machine, and you need to bring in PLC programmers and database programmers to implement some of these key items that are identified from machine learning or AI. It needs to be prescriptive. So the system needs to be able to collect data, analyze data, and based off this data, dynamically change the process without downtime and intervention that can cost a lot of money and makes these insights kind of useless if you can't actually implement them. And I guess a lot of what I'm saying here is not new to anybody. I think most of our customers understand that they need to digitize to remain competitive. But I think the majority of our customers believe or struggle to know where to start. And I hope to try and address that in the next couple of slides. So what we've been fortunate to do is build over 3,000 assembly systems. And we've taken 30 years of learning and put that into an operating system specifically for the shop floor in the discrete manufacturing space. And how we've learned all of these things and to determine what this operating system needs to do is that we've been fortunate in that we've delivered a lot of these solutions to global OEMs and global tier ones that have teams of people that determine what the process should be, what the traceability should be, what the key functions of an operating system should be. And we've been able to put that into a single platform with all of that experience built into it so that you don't need to have huge teams of people to determine and decide what needs to be done. It is an operating system that you can deploy on your shop floor that takes all of those experiences from many OEMs and many tier ones and enables you to take advantage of that. So what is an operating system? We all know, I guess, the three main operating systems out there: Windows, Apple. Apple have two different operating systems, and obviously Android is another operating system. So what are the main key functions within an operating system? So obviously there's controlling the hardware. So we all have laptops, for example, and each laptop has a set of hardware devices, including CPUs, memory, etc. And you're operating, one of the key functions of your operating system is to control and manage the hardware on your device. We obviously have a number of input devices such as keyboards, mouses. Now with COVID, we all have headphones and microphones that are all plugged into our operating system. and that is all managed by the operating system. We obviously have a number of output devices. So a screen is a good example of an output device. So it displays to you what actually is happening. A speaker is another example of an output device. A printer is an example of an output device. And why I wanted to highlight the printer is that what you see happening over here is the orange communication protocol. This is, for example, USB, would be the same standard for the printer communication protocol, USB. And essentially what's happened over the years is that these protocols have become standardized. So communication to your hard drive has become pretty standardized. HDMI is the go-to standard for communication to your screen. And so what's happened over time is that these operating systems have become standardized, and the communication to the outside world and to the hardware has become more and more standardized. And obviously you have the software interfaces. So you can put different apps on your laptop, and these apps interface and communicate to the operating system, again, in a standardized way. And so what we're suggesting and what we've developed is a concept similar to this, where there are a series of standard communication protocols that are all centered around some core functionality that is built into the operating system that enables flexibility on the shop floor. So let's go into what the concept of a shop floor operating system. So you can imagine an interface to the operating system being manual operations as an example. Very often we have fully automated stations also on a discrete manufacturing process production line. I think this is by far the majority types of machines, where we have semi-automated machines where you have an operator interfacing with the machine. It could be a robotic machine, it could be a press, it could be many different types of machines. So very often you see this semi-auto stations. We obviously have to manage the product and process data. So this is anything from, for example, the bill of materials, the bill of process, the parameters that are required to assemble that particular product, or those variants of products on that particular shop floor, need to be managed by the operating system. What we call path management and traceability, or the genealogy of the product. So path management could be a conveyor system, so tracking the product as it goes down the conveyor system. Does it need to be in this station? Should it be skipped? The AGV path management is basically directing the AGV to the right station. So maybe the product doesn't require a few stations to perform any tasks, and so the AGV can skip those stations. And all of that path management is managed by the operating system. And together with that is the traceability of the product. So as it goes through the different paths, we are recording the process and making sure that the process is correct. And as a result of that, we get the genealogy or the traceability information of that particular product. And then finally, we have the software side of things. So you obviously have interfaces to different existing systems within a factory, or new systems, could be ERP or MES systems. We obviously have analytics and reporting that's become more important. And one of the fundamental reasons why we need to take a shop floor operating system approach is that if we want to make use of the concept of prescriptive AI or machine learning, we have to take a holistic approach, because there's no point in finding insights and analytics from a machine learning model, but you're not able to implement it on a particular station. So you need to consider the whole system as one and not individual elements, because then you don't take advantage of the combination of prescriptive AI together with a semi-automated process, in addition to, for example, the process that can be optimized. And what we've done is we built this all into a product that we call Odin Workstation. And I'll go into a little bit more detail as to the functions of Odin Workstation. But there are 3 sister products that fall within the operating system: Insights, which is an analytics platform. Phantom is using computer vision to support manual processes. And Odin Engage is a feedback mechanism to everyone within the organization, from operator to CEO. So this, in a nutshell, is what we classify as a shop floor operating system. So let's go a little bit deeper. So how you can imagine the shop floor operating system is a digital backbone that runs across your shop floor. And what we're able to do is plug in different elements into this digital backbone depending on the requirement of your production process. So you can start with as little as a single station. So some of the key built-in functions in this operating system are things like variant management, BOM management. So your bill of materials can also be managed and stored within the operating system. Your work instructions, your operations, and your sequences are also managed within the operating system infrastructure. And also, just to make a note that the work instructions are not only for operators. So often this idea of work instructions is, isolated to an operator working on a particular station. But what we're doing is we're also sending work instructions to the individual machines. And I'll show you what I mean by that. So work instructions goes beyond just operators, but also is work instructions for automated machines and stations. We obviously have a planning module within the system that enables us to create the different stations and add stations and remove stations. And what's really powerful about this is that all of these functions can be done within a no-code interface. So even if your production line is a single manual station where the product comes into the station, we scan a barcode to determine what product it is, we perform a number of tests and processes on that product, while instructing the operator, in a step-by-step way, we're able to produce a production line and a product using the same operating system with just a single station. But let's say things look up and you want to introduce an additional station into the process where, for example, it's now a semi-automated process where there's a machine that needs to press on a seal and a flange as a simple example, and that machine is actually controlled by a Rockwell PLC. But the operator still needs to manage a few processes in parallel with that machine. And so we can then combine the two together where we have a manual interface together with an automated machine, and we can manage the interaction between the operator and the machine in a controlled way. I'll show you a short video of what that actually looks like in reality. Part management, as I alluded to, is really around the part tracking and data handling, as well as the the destination of the part as it goes through the line. So for example, this is a simple 2-station production line. Your conveyor or your AGV or a trolley will basically come into the first station, perform its tasks. If everything was okay, it is then enabled or allowed to work in the next station. If there was something that was wrong in this particular station, if for some reason that trolley or AGV ends up in this station, it will be disabled and the process will not be allowed to continue. So that's the data handling, the part tracking, as well as the path management. So one of the other things that is built into the operating system is what we call rework or exception management. So this is where something goes wrong. So say, for example, the product ends up in the second station, something goes wrong, the press force failure there's a failure on the press force. So what is really critical in these semi-automated processes is to make sure that that part gets handled correctly. The last thing we want is that failed part to end up in a good part bin. And so what we do is, if it's an AGV, it's pretty easy. We redirect the product to the rework area. It's a conveyor. Also, we automatically redirect it. If it's a trolley, we do rely on the operator to take it to a particular station, but they can scan that product into the rework station, and we can then display to the rework operator exactly what the failure was. And then we can also explain to them the disassembly steps or the repair steps based on that particular failure. And this is a fundamental part of ensuring the quality and the integrity of the process. Many, many unfortunate recall campaigns have come about because of this failure to manage rework and a failure to manage the exceptions on a production line. And this is something that we've experienced over the many years, and that's why we've built this into the core architecture of our operating system. Let's say things get even better and we need to introduce a new product, a new variation of the product, which requires a different machine. So this, for example, is a dynamic backlash machine. And assume that this machine was from another plant in another location. And rather than buying a brand new machine, we're able to integrate an existing machine into the production line with some minimal PLC changes. We were able to integrate that PLC, in this case, a Siemens PLC, onto this digital backbone or our operating system that enables the introduction of this piece of hardware into the production process. So you can then go into the no-code platform, update the work instruction and operations and sequences to introduce this new machine, and then the path management basically follows that process for that particular variant. And say we want to introduce some more process security, where we want to have a nut runner that's recording the torques of a particular process using open protocol, which is a standard protocol for most bolting tools nowadays. We're able to, again, connect these bolting tools onto our operating system. And as a result of that, we can obviously then have quite a detailed porting analysis, and I'll show you that a little bit later. We can obviously generate the interface to the ERP or MES systems, and then built on top of that, we can start to introduce the machine learning features onto this operating system. So what I'd like to do now is go a little bit deeper into some of these particular stations to show you what they might look like. So let's start with the manual workstation. So this is typically what it looks like. So here you see a picture of an operator interfacing with the manual workstation. And what they would typically see on the screen is this little video clip I'm about to play for you. So I'll click play over here. And what you can see is the product arrives in the station, we fetch the sequences, and then we display to the operator step by step on the left-hand side all of the processes that need to be completed, and then a pictorial instruction of what needs to be done. Here you see it's a manual input, so the operator needs to take the measurement of a bearing. He types in the value, and if the value is correct, we allow the process to continue. So this is a manual input. This is just a simple instruction. And you'll see in the next operation, the operator needs to scan a barcode. And what happens over here is they scan the wrong barcode, so we stop the process, and then the operator scans the right barcode, and then we continue. So this is an example of where we interface to hardware. So we are able to now tell the engine number marking machine to punch the right number onto the engine, and then enable the machine to type to print the right engine number and continue. Here we have to tighten a bolt. So on the right hand side, we tell the operator what tools to pick, and when the bolt was done, you can see it went green. So this is a little snapshot of what the detailed work instructions looks like for a typical operator. And all of those instructions are set up and optimized by your process engineer in the no-code interface. And I think that's really important to stress, that you don't need a programmer to be able to input those work instructions and link those work instructions to the hardware, barcode scanners, bolting tools, whatever that is. Once the interface has been set up, the rest of it is configured in the no-code interface. So I'd like to show you this idea of phantom devices. So I'm just going to play another video, and I'm just going to talk through this video and explain what phantom devices is all about. So welcome to another Machine Monday. In today's Machine Monday, I want to talk about Odin Phantom. This is our computer vision AI tool that we've developed in combination with Odin Workstation, which serves to become the Google Maps for operators. So what it does is actually uses cameras to detect devices on the station. So today we'll be highlighting the feature that we've developed, or a product we've developed using an Atlas Copco bolting tool. So we've actually developed a machine learning model that's able to detect this Atlas Copco bolting tool. The moment I bring it into a position, as you can see on the screen, we're able to detect key points of the different elements of the bolting tool. And then if the bolting tool is in the right position, I'm able to then enable the bolting tool and apply the right torque program to tighten a particular bolt. So to demonstrate that, I'm going to build and continue building this demo car. The first thing I need to do is, as the screen says, is fit the wheels. So I'll fit the wheels on.
And every time I fit the wheel, I can press the confirmation button. It tells me the next wheel to fit. So now that I've fitted all the wheels, the next step, as it says, is to obviously tighten the bolts using the tool. We've now developed the model for the Atlas Copco equivalent, and as you can see, it's telling me to pick the right socket. And what we've also built into the process is that if I pick the wrong socket, it flashes fast to tell me that I picked the wrong socket. So now I can pick the right socket, fit it onto the bolting tool, and now the flashing yellow light tells me where I need to bolt. At this point, the tool is completely disabled. So if I go to the wrong bolt, the tool is completely disabled. However, as you can see, if I go to the right bolt, the tool becomes enabled and I'm able to tighten on the bolt. And because these tools are set to a specific torque and angle, I call the right program and the bolting tool stops at the right torque. It's not telling me to bolt the next bolt, and if I go to the wrong position, as you can see, the bolting tool is completely disabled. However, if I go to the right position, the bolting tool is enabled. And that's how we've used advanced technology like machine learning and AI to create machine learning models to mimic these devices. The big advantage for us is that once I've developed the model for this particular bolting tool, and we've done it for a number of different devices like barcode scanners, verniers, obviously the Bosch ergo spin as I spoke about, we're able to reuse those models multiple times in different locations at different production lines, all for position tracking and control. Here's another machine Monday.
So that's a little overview of what phantom devices are. Basically, what they are computer vision systems that enable the process security of manual stations. What you can think of them as is the self-driving technology being used to guide and help the operator perform the tasks correctly. The next thing I'd like to quickly talk about is this interface. We call it ODEX. So this is an example of where we want to be able to create a standardized communication protocol like USB in the case of the mouse, in the case of the keyboard, in the case of the printer we spoke about earlier on the operating system. So this is the analogy I would give here is that this is our USB for machines onto our operating system. So we call it ODEX, Odin Data Exchange, and we've developed this ourselves. We've basically studied a number of existing protocols, MQTT, CoAP, and ultimately what we've done is we've taken the best of all of the worlds, the request response concept, the notify concept, the poll concept, built that into our own communication protocol called ODEX. And what that enables us to do is create libraries, and we've already created the library for Siemens and Rockwell, but in the future we can create libraries for multiple hardware devices, PLCs in this case, as well as things like Raspberry Pis, Arduinos, different microcontrollers that can all run using our library and our communication protocol. And these hardware devices will be able to connect and interface with our digital backbone or our operating system. And this is fundamental, in our opinion, to the future of digitization and integration to machines. So the big advantage of this is that we can deploy a library on, for example, a Siemens PLC. We can give some training to the PLC programmers that have developed this machine. It could be any company that develops a specialized machine. We give them some training on how to use the library, and then that device machine can actually integrate in a standardized way onto our digital backbone or our operating system. And where that plays a big role is in some of the semi-automated stations. So this is an example of a semi-automated station where you have a human and a machine working, and you'll see very clearly in this video, the operator is actually interacting with a number of different machines in the station. And so Odin is actually managing the machine, it's managing the human, and optimizing the collaboration between the human and the machine. So it looks at the different outputs from the machine, that those could be as simple as sensors, or it could be complex automated machines. And we are coordinating the machine and the human together to drive the process in the most optimal way, and to ensure the security. So we check the sensors in the station to validate the sensors are being made that need to be made. We take care of safety, for example, to make sure that the operator is out of the station so they don't get hurt. And it is the master coordinator between the human and the machine. And finally, we check some camera inputs. This is all through the PLC. Once the camera says everything is good, Odin gives the final okay, and then allows the part out the station. And so that's why the communication protocol that we've developed, ODEX, is so critical to the functioning of this human-machine collaboration, because it's very easy to make a manual station, very easy to make a fully automated station, but the majority of stations are actually semi-automated, and to try and optimize that to get the best out of the human-machine collaboration, you need to be able to talk to different types of machines and coordinate that with the work instruction that the operator sees. The final part that I wanted to share with you was all around the path management. So we kind of alluded to this, where you have a series of machines on a shop floor, and you can have a simple straight path, but depending on a particular outcome from, for example, a pinion nut machine, we want to move to a different process or a different set of machines, or we want to introduce a new variant onto the shop floor. And say, for example, there's a failure, we can redirect the AGV to the rework area. And then in conclusion, I just wanted to highlight that we've actually developed and deployed Odin Workstation operating system to multiple production lines around the world, produced millions of parts using this concept. So it's really tried and tested and brought huge flexibility and process control in these automated and semi-automated and obviously manual production lines. In a later video, I will be talking a little bit more detail on the reporting side, the analytics side, as well as the machine learning side. Please look out for that video. And if you want to find out more, please check out our website, odinmanufacturing.io. If you want to reach out to me, find me on LinkedIn and send me a message, and we can connect and take it further. Thank you.